All right, welcome to video 2 of redox. So last video you should have learned about oxidation and reduction, identifying OAs and RAs. Now we're going to move to the next part, which is basically talking about our spontaneous reactions. So if you go into your chemistry data booklet, you'll find that there is a redox table. Okay, so that redox table is on page 7 of your data booklet. Okay, so this is the table that we are going to use for pretty much every question in redox. Okay, it's found on page 7 in your data booklet. So what you're going to find is when you look at this table, it says reduction half reactions. So as we read from left to right, which is generally how we read, we should be finding that these are all reduction half reactions because all of the electrons are over on this side of the arrow, right? They're all on that reactant side. We were talking the other day and we said when those electrons are on the reactant side, it's going to be a reduction half reaction. So what that means for my agents, right? Remember we said they were backwards. So if these are all reduction half reactions, that means that all of these on this side of the arrow or this side of the page, the left side, are all going to be oxidizing agents. If we read backwards, right, which is why these all have double-headed arrows. Okay, sometimes you guys see the double-headed arrows and you're like, oh, we're back in equilibrium. We're not back in equilibrium. It's just that I could either choose to use it in one direction or I could be using it in the other. It really just depends on what I've combined it with, okay? So if we were to read, let's say, the first one backwards, now it turns into 2F minus, turning into F2 and 2 electrons. So now the electrons become on the product side. So that means when we are looking at these going that way across the page, they are all going to wind up being oxidation half reactions. So I'm going to switch over to this same table in the slide. It's a little blurry, but it's not the end of the world. So we were just saying that over here, these are all our oxidizing agents because going this way, they're all reduction half reactions. But if we chose to read that way, right, those now all turn into oxidation half reactions, which means that everything on this side of my table is going to be an RA. Okay, what you find is actually that these are in a specific order, and that order kind of matches up with the order that we saw for acids and bases. Right, if you remember our acids and bases, they went strongest to weakest and then weakest to strongest. So what we find here is for our OAs in the top left corner, and a lot of you usually like to write this in your data booklet. Usually you guys like to write SOA in the top left corner. And that's so that you know that fluorine is the strongest oxidizing agent. And then as we go down the table, down to the bottom where we have lithium, this is going to be my weakest oxidizing agent. Okay, my reducing agents follow the opposite pattern, right? Which is what we saw when we were looking at our bases. So we find that our strongest reducing agent is down in this corner, which means that our weakest reducing agent is up here, okay? So they're in order. It's important to know what that order is because as we continue to go through this lesson, we're going to talk about spontaneous reactions. Okay, and for a reaction to be spontaneous, we're looking for certain relationships between the OA and the RA. So, for us to predict if a reaction is spontaneous, we have a couple of steps that we are going to take. Okay, we're going to need our data booklet because we need to be able to find things in it. And so how this is going to work is you're going to list the things that you have. So you're going to find redox reactions are a little different than any other unit you're in, right? Normally in other units, you'd kind of look at your reactants and you'd be like, oh, I have a compound and a compound. I'm going to do double replacement. We don't actually want to do that when we're in redox. We follow some different sets, and it's kind of a good habit to start from the pretty early in the unit to start changing how you approach some of these questions, okay? So first thing you always want to do in a redox question is going to be to list all the species that you have. Okay, so you're going to look at what the question says and you're going to decode it. You're like, oh, it says I have iron metal, so I have Fe solid. And then let's say it told you you had like sodium chloride, a solution of it. You would then break that apart into individual ions, that you had sodium ions and chloride ions, because really that's how an ionic exists in solution, right? And we would do the same thing with strong acids, right? So this is kind of like what we did when we were looking at net ionic equations, right? We kind of broke everything apart so that what we would be left with is the important things. So we want to do the same thing. We want to list everything we have. Then what we want to do is we want to figure out what is the strongest oxidizing agent and what is the strongest reducing agent. And the reason we want to do that is the strongest oxidizing agent is going to be the oxidizing agent, and the strongest reducing agent is going to be the reducing agent. All the other things are going to be spectators. So it allows for me to get rid of those spectators early on, so that I don't have to worry about them at the end, right? Because sometimes you guys get a little overwhelmed with those net ionic equations and there's so much stuff happening. You're not sure when you should break something, when you shouldn't. Sometimes you start adding charges when you shouldn't, weird things like that. So your steps, you're gonna list everything. Then you're gonna go to your data table. Okay, at first this is going to take you time because you're not familiar with where things are in your data table. And you're probably going to spend more time just finding things in that table than actually writing stuff out, right? You'll find that the more you use the table, the more comfortable you do become with using it, and you'll get a lot faster at finding things. So once you have identified your SOA and the SRA, some of you I know, like I've had students in the past, they like to use, you know, you can get those little sticky notes that kind of have like the little arrowheads on them. They like to do that, and that's because otherwise you find your data table, and this one's actually in pretty good shape, but what happens, like if you had the test copies at school, this data table, like half the stuff is circled, it's written all over, and that's because when you're finding things, right, it's hard sometimes to like keep your fingers in spots. Sometimes it's easier if you have a way to mark it. So people will sometimes use like a pencil or a highlighter, but a sticky note also works as well, right? Just to kind of point out where those things are. And the little pointed sticky notes are kind of the easiest because they really highlight where you should be looking. Okay, so totally up to you. Some people like to just use pencil and then erase it when they're done. You will just find if you like mark it every time you find something, by the time you get to the end of the unit, your data booklet's, I don't want to say really hard to use, but for a lot of you, you're like, I can't even find anything because there's so much marking in it. So to figure out if something is spontaneous, first off, probably helps to know what spontaneous means. I didn't even have that in a slide. Look at that. Okay, so let's add that in. Okay, so when we talk about redox reactions, we talk about them as either being spontaneous or as being non-spontaneous. So when we say that a redox reaction is spontaneous, what that means is when we combine our reactants, a reaction just happens. We don't have to do anything. Like we put them together and we start to see something. Okay, so for spontaneous, we can say the two reactants react to form products. Okay, when we say that it is non-spontaneous, what we find is the opposite. So the two reactants do not form products. Okay, instead, they just literally sit in contact with each other and nothing happens, okay? It doesn't mean we can't make a reaction happen. It just means it's not spontaneous, right? And spontaneous means it just happens. We don't have to do anything. So in the case of non-spontaneous, they are not going to form products unless we apply an electric current. Okay, and that's because an electric current has electrons, and we can force those electrons to move in a direction that wouldn't be spontaneous. Okay, so we think about like your cell phone. When you're using it regularly, there's a spontaneous reaction happening there, right? Your battery is generating a flow of electrons, which is able to power your phone. And then eventually your battery runs out and you have to go charge it. So when you're charging it, you plug it into the wall, right? You plug it into your electric circuit, and then those electrons get pushed through that outlet into your phone and they replenish those original reactants, right? That's why you generally find that if you've had a phone for a really long time, near the end, your battery kind of doesn't work so well anymore. And it's like, oh, I've only it was fully charged 10 minutes ago, and now it's at like 20%. What's happening, right? And that's because the one reaction is spontaneous and the opposite one is non-spontaneous. And you'll see when we get into the second part of redox, we're going to talk quite a bit about voltaic cells and electrolytic cells, which basically correspond to batteries and recharging batteries, okay? So spontaneous, I put two things together, the reaction just happens. Non-spontaneous, I put two things together and nothing happens. So why I need to find the SOA and the SRA. How strong they are is going to be what determines if a reaction is spontaneous. So when I go to my data table and I find them, there's kind of two possibilities that you're going to find. So first possibility is going to be that your OA is above your RA. So either it could look like this, it could be like this guy way up here down to here, it could literally just be this one to the line below, okay? But what you're finding is that the oxidizing agent, when I find it on this side, is going to be higher than the reducing agent. Sometimes you guys get like weird and you're like, oh, it means how close it is to the top versus the bottom. It literally just means if this is the top of the page, if the OA appears higher than the RA, so this would work, this would work, this would work, all of those possibilities are going to be spontaneous reaction. Okay, and that is because we have, oh, I shifted that too far over. Can I move this? It's not working with me very well. And that's because we have the OA above that RA. Okay, and what you find is that for a non-spontaneous reaction, it's going to be the opposite. So if I have a non-spontaneous reaction, you are going to find that when you find your OA, the RA is going to be above it. So it's going to be any of these columns, right? Could literally be going one up, could be going from the very bottom way up to the top. Okay, all of those possibilities there are going to be non-spontaneous. Okay, and they are non-spontaneous because we find the opposite orientation than what we had in spontaneous. Now we find that when we find that OA, the RA is the one that is higher in the table. Okay, so list the species you have. Go to your data table. Usually what you want to start doing is identifying from the top here. Be like, do I have that? Nope, this, nope, this, nope. Oh, here we go. This is finally something I have. So here's my OA, right? And maybe you're using a little sticky note or you're putting a little arrow or something. And then you're going to go down here for your RAs. You're going to start at the bottom. You're going to start scrolling up until you find your RA. And then from there, you're going to say, well, what's the possibility? Is it going down or is it going up? Right? If it's going down and the OA is above the RA, I'm just going to say that it's spontaneous. If it's the other way, the OA is down here and the RA is up here, I'm going to say that it's non-spontaneous. So that means when I put those two things together, it's just going to sit there. Nothing's actually going to happen. There won't be any visible reaction. Okay, so let me see if we have an example somewhere. Then we'll come back to that other one. Okay, so here's how this is basically going to work. So these are the steps you're going to take, and this should be pretty similar to what we just talked about. You're going to list all your species. It can be helpful to start figuring out which things are OAs and which things are RAs, just because then it reduces how much time you're spending scanning the OA side and how much time you're spending scanning the RA side. Definitely at first, though, when you're assigning OAs and RAs, mainly the way you're doing that is by looking in your data table and figuring out, are they on the left side? Because if they're on the left side, they're an OA. If they're on the right side, then they're an RA. And then kind of going from there. So you're still at the beginning going to be spending a lot of time just looking for things in your data booklet, okay? So further we get in the unit, you're probably going to start to see that you start to recognize certain things like, oh, I know this is an OA, or I know this is an RA. So once you've assigned things as being OAs or RAs, you then need to figure out what's your SOA and what's your SRA. We just talked about how you would do that, right? Scan the OA side down till you find it, scan the SRA side up until you find it, okay? You then are going to write out those half reactions. So when you're writing out the OA half reaction, I'll go down here because it's a little cleaner, right? So like, let's say I decided my SOA was the zinc 2+. I would write that half reaction with a single-headed arrow going that way, okay, going like this. And then when I find my RA, let's say, I don't know, that it was iron, I would write it backwards. So when I write it on my sheet, I would write it as Fe solid turning into Fe2+ and 2 electrons, right? And that would have that single-headed arrow, and I would flip that around, okay? And we'll show you what that looks like in a second. But yeah, so OA gets written the same way as it is in the data booklet, turn the double-headed arrow into a single. The RA, you are going to write it flipped around from how it appears, okay? Because like we talked about in our first lesson, we always have to have one half reaction that's oxidation and one half reaction that is reduction. So at this stage, we now should have two half reactions. We want to combine them to make a whole reaction. Okay, this whole reaction that we create is going to be our net ionic equation. It's already not going to include those spectators. So for me to be able to combine them, the thing I need to do is make the electrons the same, right? Remember in that first lesson, we talked about how those electrons, when they're on opposite sides like this, they have to have the same coefficient. So I'm going to look at my two half reactions. If they are not the same for electrons, I need to make them the same. And the reason I need to make them the same is if you think about net ionic equations, when you wrote them last year in Chem 20, we never had electrons in them. If we don't make them the same, we can't fully cancel them out. We need to make sure that we can cancel out all of those electrons. Okay, so let's look at an example of what this would look like. So this comes off of the electrochemistry worksheet in your redox booklet. Okay, so it says, a lab technician stores an aqueous solution of iron 3 chloride in a nickel-plated container. So on this worksheet, it was asking you to follow those 4 steps that we talked about in the last slide, as well as it asks you to identify whether this reaction is going to be spontaneous or not. So first thing we're going to start by doing is listing out everything we have and deciding whether something is an OA or an RA. So we're told an iron 3 chloride solution. So that means we have iron 3 ions, right? Because iron 3 chloride is ionic, so we need to break that apart. We have chloride ions, right? So that's accounting for the ions that we have in iron 3 chloride. Then we have a nickel-plated container. So a nickel-plated container would just be nickel, okay? So we're only going to have ions from things that came from ionic compounds. When we're told something is plated with something, that just means we have that as an element. The other thing we have, although the question doesn't explicitly say it, is water. And the reason we have water is it says it's an aqueous solution, which means we have water. Okay, really important to list water. You're going to find that in the first part of redox, it's often not going to be our SOA or SRA, but we get into the second half of redox, it's often going to be the SOA or SRA. So really important to make sure that you're not forgetting about it. Okay, so next thing I need to do is identify which of these are OAs and which of these are RAs. So if you think back to when we were in acids and bases, remember we said we had acids, we had bases, and we had things that were amphiprotic, which meant they could do both. You're going to find we have the same thing in this unit. We have some things that are explicitly OAs, some things that are explicitly RAs, but we also have 4 things on our data table that are both. Okay, so the ones that can do both are chromium, okay, tin, iron, and water. Okay, the reason these can do both, okay, the chromium, the tin, and the iron are kind of the more obvious ones. And for them, the reason they can do both is they have multiple charges, right? So if you think of iron, because that's probably the one you're most familiar with, right? There's Fe solid, there's Fe2 plus, and there's Fe3 plus. So it's not the Fe solid or the Fe3 plus that can do both. It's that middle one, right? Which is the exact same thing we saw when we were dealing with things that were amphiprotic when we were in acids and bases, right? It was when we had the H and the negative charge that we had the ability to do both. So what you find is for iron, it's the iron 2 that can do both, because either it could lose 2 electrons and turn back into iron solid, or it could gain 2 electrons and turn back into iron solid, or it could lose 1 and turn into iron 3. Okay, we find the same thing with tin. There's Sn solid, Sn2 plus, and Sn4 plus. So that Sn2 plus has the ability to go either way. Same deal with the chromium. There's Cr solid, Cr2 plus, Cr3 plus. That middle charge of Cr2 plus can either go to Cr3 plus or it can go back to Cr solid. Then we have water. Water is just water. It does its own thing. If you look in your data booklet, there are 2 water half reactions, okay? There's a water here that's over on that Ra side. But then we also have a water down here over on that OA side, right? So that's how I can also recognize that something is amphiprotic. So there's the water. The other one we talked about was Cr2 plus, right? So here's the Cr2 plus on this side. Here it is on this side, right? And then we talked about iron 2. So here's the one iron 2. The other one is a little bit higher up in my table. It's up here. And then which one am I missing? Tin. Where's tin? So here's the one tin, right? There's tin 2. And then kind of underneath all these lines, here's that other one, right? So those are the 4. There is a little kind of, I don't want to say acronym, I don't think that's the right thing, but the little saying that some people really enjoy. It's kind of gross. It's creamy snot feels hot. So creamy for Cr, snot for Sn, feels for Fe, and hot for water. Kind of help you remember what those 4 are. You will find that in redox there is quite a bit of memorization. So sometimes some of those, like Leo the Lion says grr, and that saying, and there's others that come up too, can kind of help you remember things when there are so many things to remember. Okay, so going back to this example. So we have iron 3. So what we need to do is we need to go to our data table. I'll go to a clean one that I haven't written all over. And we are going to find, well, what are we looking for? I already forgot. Iron 3. So we look for iron 3. Iron 3 is right here. Okay, so it is on the OA side. So we know that iron 3 is an OA. Okay, now we got to find the chloride ion. So same deal, we look at our table. So chloride's on here quite a few times, right? So like here's a chloride with water. So that's a potential. Here's a chloride on its own, right? Here's a chloride with hydroxide. So I can't use this one. The reason I can't use this one is when you look at all the things we listed, we did not list hydroxide anywhere in there, okay? So no hydroxide, I can't pick that one, but I do have this one here, right, which has this, whoa, what am I doing? As an RA. Okay, now we got to find the nickel to decide what that is. So we go back to our table, we look for the nickel, it's over here. That would be on the right side, so that means that it is also an RA. Okay, then we have water. We just said water was one of those that can be both. So it could be an OA or it could be an RA. Okay, it could be both. So now we've figured out what kind of species all of these are. Our next step is to determine what's the SOA and what's the SRA. So when I look at this, the SOA is either going to be the iron 3 or it's going to be the water. So what I want to do is I want to go to my data table and I want to start on the OA side at the top and I want to start scanning down. And I'm going to keep scanning until I find one of them. So like here's a water, but this water involves OCl minus. and it lists that, so I don't have it, so I can't pick that. So I keep going, and oh, here's iron 3. So iron 3 must be my strongest oxidizing agent, right? And this is where you might want to like put a little like mark or something, or like use a little sticky note just so that you can keep your finger on it even though you're not on it anymore. So we now know that the iron 3 is going to be our SOA. So what we want to do is write out that half reaction from our data booklet, right? And the data booklet said Fe3 plus AQ plus an electron to give us an Fe2 plus AQ. Okay, so now we have one of our half reactions. We've identified the SOA. The next thing we need to do is find the SRA. So our RA is either going to be the chloride, the nickel, or the water. So we go back to our data table, and now we're going to start at the bottom of the page, and we're going to start to scan our way up until we hit one of those things. Okay, first one we hit is right here. It's the nickel. So I'm just going to scroll that. So the nickel is going to be our strongest reducing agent. So we go back to here. We now know that our strongest reducing agent is the nickel. So we're going to write out that half reaction, and we're going to flip it around from how it appeared in the data booklet. So we're going to write it as Ni solid turning into that nickel 2 plus 2 electrons. Okay, so next step is I need to combine these two half reactions. That's an awful line. Let me actually maybe use a real line. All right. There we go. Although I put an extra tick in because I'm just that skilled. Okay, so we want to combine these. To be able to combine them, I need to look at my electrons. Right now this has 1 and this has 2. We can't have that. We need to make sure that those electrons are going to fully cancel. So what we're going to have to do is we are going to have to times this entire first half reaction by 2, right? So that's going to give us 2 iron 3s, 2 electrons, and 2 iron 2s. And we need to do that because ultimately we have to be able to cancel these electrons with those electrons. And by multiplying by 2, that gives us 2 electrons here and 2 electrons here. Why we can cancel them? They're on opposite sides of the arrow. If they were on the same side of the arrow, then I would be adding them together on that side, right? So if they're both here or both here, they would go together. But like we talked about, that should never happen because it can't happen. We always have to have one half reaction that's oxidation and another one which is reduction, which is why they have to look different like this. So now that we have canceled our electrons, we do want to check if there are other things that can cancel. You'll find in this question there is nothing else that can cancel, but we definitely will get some questions further in the unit where we're sometimes like, oh, hey, I have water in both of these. I need to do something about that. So now we're going to combine what's left to generate our entire half reaction, or not half reaction, equation. So we're going to take our 2 half reactions and combine them. So kind of the opposite that we did when we first started writing half reactions. So I'm going to take the nickel and the iron 3, because they're both on the reactant side, I'm going to write them both on the reactant side. So we're going to have 2 Fe3 plus AQ, right? And 2, because we had to multiply this equation by 2 for our electrons. So plus that nickel, that's a solid. This is now going to turn into, and then we put all our products on that side. So again, don't forget that that 2 also applies over to this iron 2. I know sometimes you guys, instead of putting the 2 up here, you like to put it in front of each thing, and that's totally fine too. If you think you're going to forget that it's over here and that you need to apply it to each of those, you absolutely can do that. So we're going to get 2 Fe2 plus AQ plus that Ni 2 plus AQ. Right, so when we check this, it should balance. We have 2 irons and 2 irons, 1 nickel and 1 nickel. We also want to make sure that our charges balance. So we have 2 times 3 positives. So we have 6 positives from the iron, 0 from the nickel. So on the reactant side, we have 6 positives. We look at the product side, I have 2 times 2. So I have 4 positives from the iron plus 2 more from the nickel. So that also gets me to 6. So I have 6 and 6, so my charges are also balanced. So the last thing for me to do is to indicate whether this reaction is spontaneous or not. So this is where having marked some stuff in your data booklet can be helpful, or having like those little stickies. So here was our iron 3 as an OA, and here's our nickel as an RA. So because the OA is above the RA, this is going to be a spontaneous reaction. Okay, because when we found those things, that OA was above the RA. It's a special arrow. Well, let's pretend that's a beautiful arrow. Okay, so list, identify what's an OA, what's an RA. Go to your data table, find the SOA and find the SRA, write them out. Combine the half reactions by making the electrons the same, then decide whether it's spontaneous or not based off the location of the OA and the RA. Okay, so do spend some time practicing that. This is how we write equations for pretty much all of redox, okay? We list, find the SOA, find the SRA, and then we go from there, okay? So I think we had skipped a slide. So here we talked about creating redox tables. So this actually really should have been after that last slide, not way up there. So sometimes we ask you to do the opposite thing. So that question, we basically asked you to figure out whether something was spontaneous or not using your data table. Sometimes what we'll do is we're going to give you experimental info, and from that experimental info, we are then going to ask you to go create a redox table. So generally in these types of questions, when we're asking you to create a redox table, what you're going to find is those compounds and elements are not in your data booklet. So it's not an option to be like, well, I just don't want to do that. I'm just going to go find them in my data booklet. And there's usually 1 or 2 of you when you get questions like this that you're like, Ms. Chip, I can't find these anywhere in my data booklet. And it's like, no, they're not in your data booklet, because the point is that you have to figure it out, okay? So these are definitely more challenging than the last type of question. So what you need to do is look at the experimental info. It's usually going to give you an entire reaction. You need to then look at it and decide out of your reactants, what is the OA and what is the RA. So in the last example, we were able to decide OA and RA based off of where they were in the data table. But if these things aren't in our data table, I can't make that decision that way. Instead, what I have to do is look at what did it turn into? And in turning into that, did it gain electrons or did it lose electrons? From that decision, I can then decide if it was an oxidation or a reduction half reaction. Once I know that, then I can decide OA or RA. So a little bit more challenging because there is a lot of pieces to that puzzle, which is why I was kind of saying in that first video, really important to make sure you can recognize oxidation, reduction, OA, and RA. Okay, so this question is on the redox tables worksheet, okay? It is question number 5. So when we read this question, it says, in an experiment, 4 metals were placed into test tubes containing their respective ions. The resulting evidence is communicated by the equations below. Order the metallic ions and the hydrogen ion according to their tendency to react. Create a half reaction table and label the strongest oxidizing and reducing agent. Okay, now it's given us a series of 4 reactions. So this kind of turns into like one of those big like logic puzzle things where you kind of have to say, okay, well, I know that these 2 rank like this and these 2 rank like this. So do they go like this or do they go like this when I bring it all together in that table? Okay, so these require a lot of thinking, a lot of problem solving. They're not questions that you can just go to and be like, oh, well, here's the answer. Okay, so I'm going to walk you through how to do this. Probably what I'm going to do at a certain point is hold like a virtual classroom session just to walk you guys through a couple more examples where you actually have that ability to ask a question right away, because this is a pretty challenging concept, especially at the start of a unit, okay? All right, so how this is going to work. We are going to look at each of these reactions. So if we start with the first reaction, we have PT with 2H plus turning into PT2 plus and H2. So first step that we need to do is decide out of the PT and the H plus, which one of these is the OA and which one is the RA. So once I decide that one of them is something, I know that the other one has to be the opposite, right? So if we decide that platinum is the OA, I automatically know that hydrogen ion has to be the RA. Or if I decide that platinum is the RA, by default, the hydrogen ion has to be the OA. So really, we only have to decide what one of the reactants is, and then we automatically know what the other one is. So how we're going to do this. Here's PT solid. Here's PT2 plus, right? If we think about that, if we wrote that as a separate reaction, right, and we wrote it as PT turning into PT2 plus, where would we put those electrons to balance this equation out, right? This has no charge. This has two positives. We would be putting two electrons over on this side so that we have 0 to 0, right? Because we're putting electrons over here, we lost electrons, right? And PT turning into PT2 plus, we lost 2 electrons. When we lose electrons, that is an oxidation half reaction. If it's an oxidation half reaction, that means the PT has to be my RA because they go backwards, right? Which means the hydrogen ion has to be my OA. Okay, so let's do the same thing for the next one. Let's start by assigning all our OAs and all our RAs and then kind of going to the next step for all of them after that, okay? So we're going to do the same thing. We're going to look at the next equation now. We have C solid, and it goes into C3 plus. Well, that follows the same pattern. We went from no charge to a positive charge. We must have lost some electrons, right? We lost 3 electrons to go from no charge to a +3. If we lost electrons, it was oxidation. That means this is also my reducing agent, which by default means that nickel 2 has to be my oxidizing agent. Okay, now we go to the next one. We can look for the same thing. So let's start with the strontium solid. Strontium solid into strontium 2 plus. We just lost some electrons. Okay, you should start to notice a little bit of a pattern, and that pattern is that metals as solids are pretty much always undergoing oxidation, right? Because think about where metals are on our periodic table. They lose electrons to gain a full valence shell. They don't gain electrons. Their ions may gain electrons, but as elements, they're always going to lose them. So a pattern that you can recognize is that metals as solids are always going to be RAs, okay? And then this is going to be my OA. And then we go to the next one, and oh look, how fortunate is that? We have another solid metal. It's turning into nickel 2, so it lost electrons, meaning it was oxidized, which means it's also my RA. So something I want to point out really quickly. There are patterns to redox, but you have to be careful. Sometimes you guys create patterns that aren't real patterns, right? So I pointed out the pattern that solid metals are RAs. Sometimes you guys will look at this question in particular and you'll be like, the RA is always listed first and the OA is always listed second. That's not always true. It just so happened that this particular question had that happening, okay? They won't always do that, okay? The other thing that you have to watch for is sometimes you guys come up with things without charges are RAs. Well, that's not true for a nonmetal. A nonmetal is actually going to gain electrons to gain a full valence shell. So you have to be careful with what some of those trends you try to memorize are. It tends to be easier when you are memorizing in this unit, more so to memorize definitions than to memorize certain patterns. If there is an actual pattern to memorize, such as this one, where I was talking about solid metals being RAs, I'll point it out to you. But like I say, sometimes you guys come up with all these crazy patterns, and they're not really a real pattern, and then you basically make a question way harder than it needs to be because you think something is true even though it isn't true. Okay, so that's our first step. It's going to be to decide whether things are OAs or RAs. Okay, now that we have decided that, I'm just going to get rid of this to make some room. Now we have to start ranking some stuff, okay? So if you think about how your data table is set up, right, it is set up so that we have all our OAs on this side and all our corresponding RAs over on this side, okay? So what we're kind of going to have to do as we go through each one of these is decide where do things rank. And we may find that we can build an entire table at once, but we also sometimes find that we kind of put different pieces together and then eventually we're able to bring them back together, okay? So if we look at the first one, so PT solid with 2H+, this is a non-spontaneous reaction. The fact that it is non-spontaneous means that my RA is above my OA. So we know from this, if we want to start placing some of these into this little OA-RA table, that PT solid, which we said was an RA, has to be higher in the table than that hydrogen ion was, right? So that we have the non-spontaneous combo of OA down here, RA up here. Right? We know what goes in the other part of this half reaction because we have that over here, right? So I know that PT solid, the OA portion of that would be that PT2+, right? Because that's its partner. And when I look at that H+, its RA version must be the H2, okay? So we're starting to piece together how some of these things are going to go into our data table. So that's just from equation 1. Now we look at equation 2. So equation 2 had Ce and Ni. So I can't really keep adding to this table because I don't know where they go with respect to those two. But what I can do is kind of start a separate one somewhere else that hopefully I should be able to join them all together at the end. So now when we look at it, this one was spontaneous. So because this is spontaneous, that tells me that my OA is above my RA. So when I look at this, my nickel 2 was my OA. So I know that the nickel with that 2+ charge has to be higher on the OA side than that Ce is, right? It has to go like this so that I get that spontaneous combo, right? And then we can fill in those kind of missing pieces, right? Which would just be the regular nickel over here and the Ce3+, right? And again, I'm filling those pieces in because those are the products in that half reaction, or not half reaction, that equation. So now we have two pieces to the puzzle. We know that PT2+ is above H+, we know that nickel 2+ is above Ce3+, but we don't yet know how those pieces are going to come together. So now let's go look at equation 3. So equation 3 was strontium with Ce3+. Okay, we have Ce3+ in our table right here. So hopefully we can use that to help us figure out where some pieces are going to go. So this one said it was spontaneous. So it's spontaneous, that means my OA is above my RA. So I already have Ce3+ placed in here as an OA. So now I know that the strontium as an RA has to go below it because the OA has to be above the RA. Its partner, that's going to go over on this side, is going to be that Sr2+. Okay, so we're getting closer to having a completed ranking. I'm going to go to that fourth equation now. And hopefully that fourth equation is going to bring these two separate pieces all together. So we look at the fourth equation. It says it is spontaneous. So that means my OA has to be above my RA. So the OA is the H+, which is here. So that has to be above the nickel as an RA. So I know it has to go like this. So now when I look at this, I should start to see that this whole part here is basically going to come in down here, right? Because if I know that platinum is higher than hydrogen, and now I know that hydrogen is higher than nickel, and I've already established that nickel is above the cesium and above the strontium, I now know how all of this has to go together. So I should write out an actual half reaction table, because that's what it's asking for, not just a random ranking. That random ranking was just to kind of help us reach that point where we would be able to do that. So how this reduction table is going to look. We're going to start with the platinum. So we're going to have the PT2 plus AQ plus 2 electrons. Why 2 electrons? Well, look, it's PT2 plus a PT with no charge. I need 2 electrons. Then we should have that double-headed arrow. Sorry, I can't really draw a double-headed arrow on here, so I'm going to draw a messed up double-headed arrow, but you guys can draw like the little equilibrium arrows. And then that's going to turn into PT solid. So there's my first one. Now my next one is going to be H plus and H2. So because this has a 2 and this doesn't, we're going to have to write it as 2H plus. Okay, we're going to have to add 2 electrons because we have that 2 positives from this. And then this is going to turn into, still in that mode. Sorry, I'm having issues. Here we go. Okay, that is going to turn into that H2 gas. Okay, so what's going to come after that is now going to be that nickel half reaction that we had up here. So we're going to have the Ni2 plus AQ plus 2 electrons, giving us that Ni solid. And then our next one is going to be the Ce3 plus. Okay, this one gets 3 electrons, and the reason this gets 3 electrons is we have that 3 charge, right? And then the other one has no charge. So we're determining electrons based off of balancing charges. Here we needed a coefficient because this had that H2. The other ones don't need coefficients because they don't have any of those subscripts that we need to worry about balancing. All right, and then the last thing was that strontium. Okay, it's going to gain 2 electrons, and it is going to turn into the SR solid, right? So now we have created our own reduction table, and in creating this table, we've arranged it so that our SOA is up here, and our SRA is down here, right? So it's following the same setup that we have in our data booklet, right? The difference is, a bunch of these things are not in our data booklet, which is why we have to actually figure out where they would place with respect to each other, right? And it kind of works out to be in this big puzzle where you have to puzzle through it all based off of what you have and what you don't have, okay? So the more common way that you will see this question, or at least now the more common way, you still will definitely get it like this, but the other way they will often give it to you is more as lab data. So normally at the start of this unit, we would go to the lab and we would do a quick intro to redox lab, and you would take 4 strips of metal. So you would have what do we usually use? We use a zinc strip, a silver strip, a magnesium strip, and there's one other metal that of course I'm totally blanking on what it is. But yeah, you'd have another metal. And then what we have is we have little solutions containing all of those metal ions. So there's a magnesium one, a zinc one, I think it's copper that we use as well, and then silver. And so then what we do is we take all our strips of metals and we put drops of all 4 solutions onto it. And then what we do is we generate a table that kind of looks like this. Okay, where in this table, when we put a check mark, that means we saw a reaction. So when I took my solid strip of aluminum and I put aluminum solution on it, I didn't see anything. But when I put zinc solution on it, I saw evidence of a reaction. So we put a little check mark. And then when I put the magnesium on the aluminum, again, I saw nothing. And then when I put the silver ions on, I definitely saw a reaction. I put a check mark, okay? So these are actually way easier than the last one. Okay, the reason they are way easier is what you find is either all of these are OAs or all of these are the OAs. And once I can figure out which side is OAs and which side is RAs, the rest of the question comes together really quickly and easily. So let's just look at the aluminum turning into Al3+, right? If we had aluminum turning into aluminum ions, we would be losing electrons. Losing electrons is defined as oxidation, which is telling me that all of these have to be RAs, which means all of these have to be OAs. So once I know that, this becomes a pretty quick question. Some of these questions will be like, oh, rank the OAs from strongest to weakest. So if I was asked to rank the OAs from strongest to weakest, once I know that these are all my OAs, I'm just looking for which one has the most check marks, right? So Al3+ has 1, zinc has 2, the Mg2+ has none, and silver has 3. So that means the silver ion is the strongest oxidizing reagent because it reacted with the most things, right? So if I was ranking my OAs, right? So if I was ranking OAs from strongest to weakest, my order, that's not how you spell weakest, would be the silver ion first because it had the most check marks, then the zinc ion because it had the next most check marks, then the aluminum, and the last one would be the magnesium, right? And if it had asked me to rank, I don't know, let's say the RAs instead. Let's say it asked you to rank the RAs from strongest to weakest. Well, now I'm just going to look at the RAs, right? So my RAs are over here in my table. So aluminum reacted twice, zinc reacted once, magnesium reacted 3 times, and silver reacted none. So magnesium would be my strongest reducing agent. Then it would be zinc. Then it would be, wait, no, that's not right, sorry, magnesium, then aluminum, then zinc, and then silver. You should notice these are complete opposite orders of each other. And that's because if we actually put these into a standard reduction table, we'd have the silver with the silver, well, the silver ion with the silver, and then we would have the zinc, and then we would have the aluminum, and then we would have the magnesium. And so because we have those opposite orientations for strongest to weakest, that's why we find that pattern, right? So these tables are way faster and easier because really I only have to identify the OA and the RA one time. Then I know that all of this or all of this is one thing. And then I'm looking at how many check marks I have. Where do I have the most, going down to the least. Biggest issue you guys tend to have with these questions, you don't read the question. You like to assume that it always says rank the OA from strongest to weakest. Sometimes it says that, sometimes it says from weakest to strongest, sometimes it asks you to rank RAs. They're kind of all over the place with what they can ask you. Apparently my slides are just entirely out of order on this. And this definitely should have been up near the top. We already wrote this slide out. So yeah, that kind of concludes your spontaneous and non-spontaneous. There's a lot of stuff to it. Sorry this video was so long. But there's a lot of content in redox, and it takes a lot of practice to make sure you really have that nailed down, okay? So in your booklets, you should have some questions on building data tables, which would be, and the spontaneous, non-spontaneous stuff, which would be the stuff that would accompany this particular video, okay?